Hi everyone, we're the JSNL team and we are studying on the topic OLED screens investigation and evaluation. My name is Sage.
Hi, I'm Liam.
Hi, I'm Nate.
Hi, this is Jeff.
So, we're going to talk about why OLED. The course topic is multimedia, which is a diverse subject concerning the implementations required to display media. Video screens are one of the main ways of displaying picture and video. Over the years, a variety of technologies has been employed from CRT to the futuristic micro-LED. Organic light emitting diode is a type of immersive electronic luminescent device. Ever since OLED was invented, it has been gradually taking over LCD to dominate the display screen market. Today, OLED has become one of the major multimedia displays used. OLED features high definition, long life, and low energy consumption. These traits make OLED an ecologically friendly choice. What is OLED? An organic light emitting diode is a light emitting diode in which the emissive electronic luminescent layer is a film of organic compound that emits light in response to electronic current. Then, what is our research about? The main topic we'll be focusing on will be the design of OLED, the input-output of OLED, technologies that use OLED, and differences between OLED and other type of popular displays. In order to learn about OLED, our team has been surveying on topics and got results. This representation will be separated into 5 main parts: the OLED structure, the OLED control, the implementation, and the comparison and conclusion. I'm going to go through the first part, OLED structure. OLED is made of emissive electronic luminescent crystals, which are materials emitting light when a current is applied. This is the foundation of OLED technology. From the diagram in this slide, you can see that there are 8 main components in an OLED. So I'm going to introduce one by one. The first one is substrate. It can be plastic, glass, or metal. It is the foundation of OLED. The next one is anode. It may or may not be transparent depending on the type of OLED. It is positively charged to inject holes into the organic layers that make up the OLED device. The next one is hole injection layer. Hole injection layer deposited on top of the anode. This layer receives holes from the anode and injects them deeper into the device. The next one is hole transport layer. This layer supports the transport of holes across it so that they can reach the emissive layer. The next one is emissive layer. Emissive layer is the heart of the device and where light is made. The emissive layer consists of a color-defining emitter dopped into a host. This is the layer where the electronic energy is directly converted into light. The blocking layer is commonly used to improve OLED technology by confining electrons to the emissive layer. The electron transport layer supports the transport of electrons across it so that they can reach the emissive layer. The cathode may or may not be transparent depending on the type of OLED, and it is negatively charged to inject electrons into the organic layers that make up the OLED device.
Hi, I'm Liam, and I'll be going into part 2 of our report. There are different types of OLED. The first one we're going to go into is bottom emission. Bottom emission OLED devices are devices where the light emitted passes through the transparent bottom electrode as well as the substrate that the panel was created on. AMOLED are typically created with a non-transparent bottom substrate, leading to light being blocked if the device is bottom emission. So this is generally used for the other type. The second type of OLED we're going to go into is top emission. Top emission OLED devices are devices where the light emitted exits through a lid that is added after creating the device. These top emission OLED devices are better for AMOLED due to the non-transparent substrate used under most AMOLED panels. The next one is transparent OLED. Transparent OLED devices are made by using a transparent substrate on both the top and bottom sides of an OLED device. This allows the device to have both bottom and top emission properties. This type of OLED is typically used in heads-up displays and augmented reality applications. The top picture on the slide is one of these devices. The next one is stacked OLED. Stacking the red, green, and blue subpixels instead of placing them side by side creates what is known as stacked OLED. This leads to greater color depth and reduces the gap between pixels. The last one is inverted OLED. Inverted OLED places the cathode on the bottom attached to the substrate. This device is an attempt to lower the cost of OLED by making use of an amorphous silicon and a TFT. A TFT is a type of switch transistor. In the second picture, red and green stacked OLEDs emit from both sides of a glass substrate. The green OLED emissions are reflected by a mirror. The next part we'll go into is OLED fabrication methods. The first one is PVD, physical vapor deposition. It's a group of vacuum coating techniques used to deposit thin films of various materials on different surfaces. This technique is based on the formation of vapor of the material to be deposited as a thin film. The material in solid form is either heated until evaporation through thermal evaporation or sputtered by ions in a technique known as sputtering. This can be done with a sample of an ion beam from an external ion source. Thermal vapor evaporation of small molecules is carried out on a glass surface. Multicolored displays are made by properly met shadow masks for depositing RGB emitting material. The next technique is screen printing. So it has a lower cost and higher throughput through screen printing. They have great promise in the fabrication of OLED devices due to this. In particular, inkjet printing is another way to deposit the organic layers, especially organic polymers. In this method, we can simply use a modified inkjet printer, and the organic layers are sprayed onto substrates like ink on paper during printing. The next part is OLED control. How does an OLED emit light? To make an OLED emit light, we can apply voltage across the OLED. Electrons enter through the cathode and holes. Absence of electrons becomes prevalent in the anode. This transmits to the emissive layer and the holes and electrons meet. As the meeting of electrons and holes occurs, photons are released, creating visible light. This process is completed row times column amount of times across OLED screens as each pixel in a single OLED lights up. I think that's it.
Hi, I'm Nate, and I'm going to introduce the OLED control types. There's two types. The first one is PMOLED, or passive matrix OLED. The original way of controlling OLED screens was PMOLED, in part due to its simplicity. Good contrast with deep blacks is one of the highlights of OLED technology and is prevalent in PMOLED. PMOLED displays operate by writing one row of pixels at a time. PMOLED is passive matrix because only one line of pixels is on at any time. The lines refresh at high frequency in order to trick the human eye into thinking the entire screen is lit. Unfortunately, if the lines are drawn at a normal light level, the average light given off by the screen will be the light of a single row divided by the number of rows. In order to make PMOLED screens bright enough, the single lines need to be driven with much more voltage so their average light is on par with the other screens. This method has two big problems. The high voltage causes a lower lifespan and the power consumption is greatly increased. And these problems are negligible at small screen sizes. The amount of voltage needed to drive each light is based on the total number of lines. A rough estimate for the maximum allowed screen size would be 200 times 200 pixels. At this point in time, the main reason to use PMOLED would be its low cost due to an easy production. AMOLED is the other type, or active matrix OLED. It is also associated with an addressing scheme. For a rows times column display, to address the display in rows plus columns, unique addresses are used. Row is selected with a signal VR, and columns are selected individually with a VC in order to turn pixels on. Color PMOLED works similarly, but there are more OLED in a single pixel leading to wider rows. AMOLED was created after PMOLED in order to solve some of the issues around PMOLED. AMOLED differs from PMOLED in that the diode is connected to a transistor and a capacitor. This technology allows AMOLED to have memory and maintain its state while the other diodes are being addressed. These changes lower the amount of voltage required to drive the diodes, increasing the lifespan and the energy efficiency. Addressing is done much the same way as PMOLED with the row plus column unique addresses. Here's a demo that we've written that will show you the idea between OLED or AMOLED and PMOLED. There's two buttons on there to cycle between AMOLED and PMOLED. And you can use set delay in order to change the refresh rate. The patterns displayed are the numbers 1 to 9 as would be seen on a digital clock. The current number can be seen in the current state. The line being refreshed is visible under current line. I think that's all. OLED implementations. We'll mainly discuss from three parts: smartphone, television, and heads-up display, or HUD. For the smartphone, there are several screen technologies currently in use today, and each smartphone manufacturer has its own preferences and taste for their devices. The OLED display has an advantage that places it above the rest, especially compared to its main competitor, which is LCD. Mobile phones that boast OLED screens are rapidly becoming more prevalent, with an estimated 250 million AMOLED screens produced in 2015, mostly to satisfy demands from mobile phone companies. Samsung has been using AMOLEDs in its high-end phones for many years, and most phone makers are starting to adopt OLED displays, including Apple, according to reports in 2017. For television, as of 2018, the only company that produces commercial OLED TV panels is LG Displays, and LG Electronics is leading the OLED TV producer, although LG also supplies OLED panels to other companies including Sony and Philips. Reviews of OLED TVs are terrific, and most experts and consumers agree that those OLED TVs are the best TVs ever produced, with virtually perfect image quality and beautiful form factors. Heads-up display, referred to as HUD normally, was first introduced in the 1940s to help fighter pilots during the war. HUD is now being used in other vehicles, and there's experimentation on using HUD on glasses and scuba goggles. OLED is most commonly used for the pixels of the HUD. One of the biggest issues with HUD is that you need the display to be transparent when pixels are not producing light. When turned off, transparent OLEDs are up to 85% as transparent as their substrates, which makes them a perfect candidate for using HUD.
Okay, this is Jeff. In this section, our team compared three other modern screens to OLED. Those screens are plasma, LED, LCD, and micro LED. OLED screens are known mostly for their high contrast and brightness. One of OLED's biggest weaknesses is its short lifespan due to the blue pixels having a much shorter operating lifetime. Now I will introduce these three modern screens. Plasma screens first became commercial products in 1997 and were discontinued in 2013. Since OLED screens first appeared on the markets in 2008, the OLED screens are considered superior to the plasma screens. The first major difference is the resolution quality. Plasma screens can reach 1080p or 4K resolutions, whereas OLED screens can, which quickly become a bigger issue as video and image quality continue to improve. OLED screens also have a higher brightness, which creates a larger contrast. Contrast is extremely important as it is more noticeable to the human eye than color and even resolution. Plasma screens use more electricity than OLED screens of the same size and also need to be much thicker than the OLED screens. However, not everything about the plasma screens is worse than the much newer OLED technology, as plasma has a much longer lifespan as well as being the less expensive option. The next screen is LCD. LED LCD screens is more commonly known as just LCD screens are considered to be the standard for commercial screens available today. They overtook plasma screens in the year 2007 and are now competing with OLED and micro LED for screen option. LCD screens can reach the same resolution as OLED screens, but is considered to be lower quality than OLED. The main reasons that LCD screens are lower quality is due to the LED backlight that is used to illuminate the crystals that produce colors. Since each pixels in OLED screens produce their own light, they can produce darker shadows of black than LCD screens can, which creates a higher contrast. Another thing that LCD screens suffer from is uniform contrast, which is how consistent the brightness is across the entire screen. Viewing an LCD screen from any angle that is not straight on noticeable lowers the quality of that screens, whereas OLED screens do not reduce quality based on viewing angle. The lower brightness of LCD screens use less energy than OLED screens and also leads to a longer lifespan than OLED screens. The prices on OLED screens is much higher than that of LCD screens, which is one of the main reasons that OLED has not fully taken over the commercial screens market. Micro LED screens are a very new technology, with commercial screens appearing on the market for the first time this year. These new screens are the only ones that can emit a higher brightness than OLED screens can, and are also more energy efficient. Despite the higher brightness, micro LED has a longer lifespan than both OLED and LCD screens do. OLED has less flexibility is in the sizes available, whereas micro LED can be fitted to any size that is needed. One thing that all other screens have in common in burn-in, something that occurs when an image is displayed on a screen for too long and causes the next image to retain part of the previous one. Micro LED does not have any chances of burn-in. The viewing angle of micro LED are slightly better than OLED as well. The drawbacks of micro LED screens comes in the form of production. Each pixel has to be made and careful placed individually, making the process expensive and time-consuming. OLED screens can be produced much faster, which also means that they are available for much lower prices than any micro LED screens.
Now that we have reached our conclusions, in summary, OLED is the screen technology of the future. Currently, OLED technology is mainly used for making small displays like mobile devices, like cameras, phones, and players. OLED displays provide better power efficiency and brighter pictures, hence they are ideal for gadgets powered by batteries. Secondly, compared to LCD, OLED displays are quite costly and they are still limited to use in small devices. Even though it is possible to manufacture larger OLED screens, the process is costly and difficult. In the TV segment, only Sony and LG has produced certain models with OLED displays, but mass production at competitive price are still not happening. On the other hand, OLED technology is widely being used in the lighting industry, with Philips and Lumitech manufacturing OLED panels as a premium light fixtures. In the near future, we can expect many devices and applications of flexible and transparent OLED, such as TV screens that can be rolled up, curved displays, transparent displays embedded in windows, displays that can be worn. If you are interested in our research, you can do some further exploration on our website, or if you have any questions, you can send us by email. Thank you so much for listening to our presentation.